Welcome to the Society of Cost Engineers. We are a organization designed to promote cost engineering discipline. Membership is free. Basic membership is free, I should say, and a premium membership gets you access to archived materials, ability to post jobs, ability to post resumes, a bunch of other things. That is only $25 a year. Um, Today we will be hosting a webcast by Doug Howarth from Hypernomics. Doug is also a board member for the Society of Cost Engineers. I think if you pay attention today, you will learn quite a bit. Doug is a very, very intelligent person, and I'm very proud to have him as a member of our team. So go for it, Doug.
Jerry, thank you. Thank you, everybody, and welcome to Hypernomics. And so let me tell you a little bit about what Hypernomics is and the software called HypernomicA that goes along with it. We're going to start this by looking at what classical economics tells people. And then we're going to take a quick look at Hypernomics, just a very brief overview, and then we'll get into the details of it going forward here. But we're going to look at something called the law of value and demand, and then compare that to costs. And then we're going to get into the HypernomicA software. And we'll show you how we can figure out the responses markets have to features, calculate the demand, and do the 4D analytics, and end up with a summary here. So classical economics, some of you may have heard of the law of supply and demand, and Paul Samuelson said that the equilibrium point must be at the intersection of the supply and demand curves. And what he means by that is that there's an upward sloping supply curve and a downward sloping demand curve, and that they have a single equilibrium point somewhere in the middle. The reason you might have said something like that is that that approach does work for a few parts of the economy, the commodities being one of the most notable examples of that. Here there's a upward sloping supply curve for iron ore. The iron that comes from Australia is in orange, the one from Brazil is in blue, and you can see as various mines come online, there's the cost of the mines, and they have a little bit of profit built in. As they go up, there's an upward sloping supply curve. But the law of supply and demand may not affect something more complicated like electric cars. So how's the market for electric cars work? Well, let's take a look. So the mass-produced electric car market began just a few years ago with a single car being sold by Mitsubishi, one unit sold back in July of 2009. And then as the year wore on, well, they made more, and then they made more. And so this would actually satisfy the single equilibrium point by Paul Samuelson. But as time marched on, as you probably know, there became more and more models that were introduced into the market here. And then something formed here that we call the demand frontier, an outer boundary that formed with the market. And so what we've discovered is that these demand frontiers form for all sufficiently mature markets. And there's various forms of them. We're going to look at a couple of them today, but they turn out to be very crucial for whatever market you're trying to enter. So in 2013, for example, there were these electric cars here. There's the first year they were produced. There's a quantity, a range, and a horsepower and a price. So if you were to plot horsepower versus price, you get this chart here up in the upper right-hand corner where you see that generally as horsepower goes up, the price goes up along with it. And then if you were to plot range in the same fashion, as you add range, the price goes up. And usefully, what we could do is if we wanted to, we could reverse the axis and show the axis going from, instead of going from left to right, and we can make it go right to left here, and we can get the same kind of response. So these product features drive prices. Now, what holds up these prices? Well, if you were to plot both of the horsepower and the range at the same time against price, you discover that the electric car value is a function of both of those things. And this is a statistically significant plane that appears for both of those elements there. And at the same time, there was a demand frontier for the electric car market. Now note that this value space here in this demand plane both share a vertical price axis. And so what that means is that these two systems abut one another along the price axis. So every point here has a matching point over here. And then cost, which we'll get to later, cost rise as you add features. So as you add more horsepower and add more range, you've got more cost, but they also fall with increasing scales due to learning. And so if you were to then go ahead and plot these axes, you discover that you have four of them working here at once. You've got value attribute 1, which is in this case range, value attribute 2, which is horsepower, price, and quantity. And note that this is a different coordinate system. This is an extension of a Cartesian coordinate system. So instead of having an origin of 0, 0, or 0, 0, 0, this origin is 0, 0, 0, 0. These two are coded in green, relating to the value space. This is coded in gold, showing that there's a certain price to these things, and this is coded in red, relating to demand. So you might ask yourself, what is hypernomics? Well, it's the study of market forces in 4 or more dimensions. So it comes from the root hyper, one meaning of which is existing in more than 3 dimensions, and the prefix root hyper, rather, and then the root nonomy, meaning a system of laws governing a certain field here. So the primary observation of hypernomics is the law of value and demand, which states that the product features drive value, value drives price, price limits quantity sold, and quantity sold is a feature. And the reason it works is because people in markets as buyers, they basically self-aggregate their behaviors. They don't all do the same thing, but they do their behaviors within a range of responses that makes it so you can describe these things mathematically. And so this gives us some hypotheses that we can test. So we're going to look at the value, demand, and cost in that order here and check out how we can establish some mathematics that shows how these things relate to one another. So when it comes to value, we say that features drive value. So we hypothesize that value means simply getting more of what you want or getting less of what you don't want. If you get more of what you want, the prices go up, and if it goes in the other directions, prices go down. So this is a hypothesis. We want to be able to test for that then. So how can we go about testing for that? Well, value, and again, in our vernacular, means getting satisfaction. And so Mick Jagger famously said he can't get no satisfaction. But you see, Mick in 1967 is about to take a helicopter ride here with Marianne Faithfull. And then just a couple years ago, he's popping off of another helicopter here. So you might ask yourself, which helicopter features would give Mr. Jagger some satisfaction? And that's what we want to do here. So we might suppose that it's something like capacity. How much could anything hold or carry? How comfortable it might be, how safe a product might be, how flexible it might be, some amount of power, how far it can go, how fast it can go, and how durable it is. And so these are just a few of the things that we think that might give satisfaction. So we might want to test for that when it comes to helicopters. So we're going to consider the differences between the 2 helicopters you saw there. We believe the first helicopter you saw was in 1967 with Mr. Jagger was this Bell 47 Ranger. And then the second one was this Airbus H175. And so how might we describe the differences between one of these and the other? Well, first you might just go into the interior. So the interior of this Bell was pretty cramped. It typically had 3, maybe occasionally 4 seats in the back. The pilot sat here. But the Airbus in a VIP configuration can carry up to 8 people, 6 to 8. And if it goes offshore, as they use them frequently to take people to offshore drilling rigs, especially in the North Sea, well, they can carry many more people here. So seats are probably a poor proxy for capacity. We would prefer to have the volume, the number of cubic feet or cubic meters in a space that we could measure. We couldn't get that uniformly for all these helicopters, so we used internal useful load in pounds and as a proxy for capacity. And then you might want to study the drivetrains. So this Bell helicopter had two main rotor blades and it had one piston engine here, whereas the Airbus has these five main rotor blades and two turboshaft engines. This could only go 84 miles an hour. This can go roughly double here. Those are some features we might want to take a look at. Also, comparing the cockpits. This is a dated instrument panel. Of course, it was modern for when the time it came out, but not anymore. And so this is incompatible with night vision goggles. But the Airbus helicopter is compatible with night vision goggles. And night vision goggles allows the plane to be used at night, making the plane more flexible. So what we might hypothesize then is you've got these features. You've got seats that add comfort. We've got engines that add safety. Engine type, the turboshafts have a better power to weight ratio. They offer more horsepower overall and make it a safer environment. Then the cruise speeds are noticeably different. And then the main rotor blades. Turns out that if you have more rotor blades, the air is disturbed less because the blade isn't as big. Each blade is not taking up as much of the load of the plane. When you have two rotor blades, they basically have to each pick up half of the weight of the plane or more. But when you have five, you're dividing the load for each rotor down by that proportional fraction. And so the smaller, more numerous blades disturb the air less. And then this night vision goggle compatibility allows the night flight. So how can we maybe quantify these differences in others? So here's where we want to go off and look at these elements in what we call Hypernomica. Hypernomica is our patented software that allows us to look at data in 4 dimensions here. So what we've done here is we've created a database that's got 77 miles. This is from 10 years ago and has 49 independent variables. And so people might say, Doug, how do you know what variables are going to affect the value? And what we would say back to them is, well, we don't. So we have to kind of guess at how many might be important. And in this case, we guessed, a sizable number, and then we narrow it down to the ones that actually do provide an impact. So this is what's known as our database tab in Hypernomica. And then this database tab also lets us pick thresholds for key statistics. So there's an R-squared that shows cross correlations, a CV index here, a mean absolute percentage error threshold, and then the p-values for each of the individual variables, which we've set here to 0.05, which is kind of standard throughout the industry. So these are thresholds, and then along with that, we also have filters. So in this case, what we've done is we've taken out a Russian helicopter, which Russian helicopters and Russian aircraft tend to crash more frequently than other planes. So we took it out here because we didn't have any crash data for the industry. We also took out instances where we didn't have range data for a couple of the aircraft. And then we also did 2 different quantity estimates for the upcoming several years here, where we figured out how many planes are going to be built over a certain period. And we had 2 different intervals that we were looking at. We were looking at 02 to 23 and then another period here. So the first thing we could do then is pairwise comparisons in our scatter plot tab here, where we compare here internal useful load, cruise speed, takeoff horsepower, and the number of dollars that they think's fetched for utility helicopters. Down the pairwise comparison for comparing like to like, what we've done here is just made a histogram how the variables distribute across this particular feature here. So you can see internal useful load. There's a few that are very light and they peak off. So it kind of looks log normal. This has got a distribution that's kind of skewed to the left. There's only one plane that can make it this fast. Here's horsepower, and then here's dollars. And this kind of gives you an idea how the demand curve is going to shape up. But the reason you do something like this is you're comparing maybe internal useful load in this direction to utility dollars, and you see that there's a correlation to this from, as you get more internal useful load, the dollars go up. As you get more speed, the dollars go up. If you get more horsepower, the dollars go up. And so this scatter plot tab would permit dozens of comparisons at the same time. So then we might want to move off to the model tab and then pick a dependent variable, in this case corporate dollars. And then this gives us independent variable choices that the software is already ranked in terms of their correlation back to the dependent variable that we're looking at here. So it works out in helicopters. There's a whole bunch of different categories. There's corporate, utility, law enforcement, oil, and so on. So each one of the prices correlates pretty well to the other prices. We're not going to be concerned with that, but we may be concerned with things like horsepower, internal useful load, and the like. And we're going to choose, we have a regression types here. We have power form equations, linear equations, or polynomials. And we're going to choose some power equations here. So as soon as we pick an independent variable here, which we pick internal useful load, we instantly get an equation here that suggests that the price of a corporate helicopter is a function of this constant times the internal useful load raised to this power. This ping factor that we have is a multiplicative factor on the constant. It was invented by Dr. Shuping Hu, who was a mathematician working out of Galarath for years, and she posted up some very interesting mathematics that she left to the groups for us to use and everybody else. So we've included her adjuster here. It adjusts upward the constant for variation off the mean. So basically, the lower your equation, the more the constant is going to be adjusted upward. So we've added that here. And then we've got these series of residuals down here, which can either be in unit space or standard space here that we're seeing here, these in standard space. And so what we might be able to do then is say, well, that was pretty good. We've got a nice R squared already. We've got a mean absolute percentage error of 24.7%. We may want to see if we can get better than that. And in this case, we've added engines, the number of engines here. And it turns out that drops the mean absolute percentage error and increases our adjusted R square. And then we add in speed, cruise knots here, and we get better again. And we add in the number of blades, better still. Then I add in night vision goggles. And then finally, when we get to the sixth variable here, this will scroll down when we get to that screen. Well, we've got a 6 independent variable equation that's describing this stuff pretty well. We've only got a little less than 2% of the variation undescribed here. And then if you run your cursor over these observations, as we've done here, you might find some helos that are overpriced and some that are underpriced. So here is the Bell 505, and we find that to be underpriced. And then you can view your regression results here. And if you wanted to, you could export the analysis of variance off to a separate sheet and then do some work with that. Now the Analyze tab lets you see the effect of these variables here. So what we've done here is we've taken that 6 variable equation we've had here. We've set the internal useful load, the engines, the speed, number of main blades. And we've said that it doesn't have night vision goggles and it doesn't have a turbine engine here. And so this is saying that a helicopter with this configuration is worth about $4.23 million. But if we were to give it a night vision goggles, the price goes up. And if we offer a turbine engine, the price goes up. So let me show that again in 2 steps here. So here we're adding night vision goggles, the price goes up to $4.9 million. If we add a turbine engine, the price goes up to $8.9 million. And then if we go from 1 engine to 2, here's the price with 1 engine, $8.9 million. We had a second engine, it takes the price up nearly to $14 million. And then you see this line is still below the average of all these points here. And you see we have 2 main blades here. So if we go from 2 main blades to 3, this goes up. And it goes up if we go to 4, and it goes up if we go to 5. And now we're up to a helicopter that's worth $20.8 million. And we call this little guy here the meatball. You notice this is the same for all these different charts here. And this lets you can scroll these things in here using these slider bars and actually dial yourself into open market spaces and figure out what the market wants, doesn't have, and can afford. Also, very importantly, any axis can be swapped for any other here. So what I've done in this case, I've clicked on this and we've got 49 variables. So the first 30 are depicted here. And if you wanted to get the next set of variables, you would go to that selector there. So how well does this work in practice, you might ask yourself? Well, in 2013, when we came up with this thing, we were looking at the Bell 505. It was about to be released to the market back in 15. We were looking at it 13. Its initial price, as you can see here, was just a little over $1 million. And you got some data on this. This data came out later. We thought it was $1 million back then. They said it was just a little over. It turned out this was the actual price that they were charging. And so what we did was we made 3 utility helicopter estimates. And so here's an equation that we came up with that said that dollars is a function of all these variables here. And you see it had some very stellar statistics in here. This is comparing a baseline in green to what the changes might be in these other elements here for each one of the independent variables. And when you take these 3 equations that we had, each one said that the price seemed to be low. So one said it was low by this amount, another one by this amount, another one this amount. So our analysis suggested it should be 1.34 million. So time has passed since then. How do you test that? Well, what we did was we went out to the internet and discovered that you can find prices for used Jet Rangers here. And so these are the prices that were posted. Now, these are all in current year dollars, but if you were to take a calculator and then regress back, you'd find that the 2013 price was as shown here. And the average of these guys was 1.33 million, which is very close to our estimate. Now, if you also figure out what they would have done, we're going to show you some more about demand here, but what they did do was they built 400 of them at a certain point for 1.07. We think they should have built fewer for a higher price. The revenue would have been here. They would actually have more revenue had they built fewer with a higher price. And if you assume that their first unit cost was this, and they were learning at this rate here, well, they could have had less cost building this thing here. So if you take the sum of all this stuff, we're going to show you here in a second. So the Bell celebrated their 400th delivery in August 2022. So they had 400 at this price here. They made that amount of revenue. We figure their cost was roughly this. We figure they made roughly that. We think instead they should have built fewer at a higher price, made more revenue, expended less, then they would have made $50 million more. So that's the reason you do something like this. So all that stuff was based on the value of a helicopter. So now we're going to go to demand. And demand applies to commercial products and applies to military products. So in 2018, the United States decided to go through Lockheed Martin to build this program called the Arrow, an air-to-surface missile which was hypersonic. Now, the Congressional Budget Office estimated that if you build 100 of these things, that each copy would be $18 million, and with a program cost of this. So you might ask yourself, how feasible was this feasibility study? Well, several years before, I went out and done a study that showed that here was the 20-year buy from the beginning of 1997 to the end of 16. These are all the air-to-surface missiles. I should say unclassified air-to-surface missiles. I don't know if we have any classified ones. But these are all the unclassified air-to-surface missiles that we had in inventory here. And very interestingly, this is very highly correlated at the frontier, had a very low standard deviation. So what does this research mean to the Arrow program? Well, let's look. The Lockheed Martin people had a first unit price of $42.2 million, which very incidentally happened to be just about the constant for this curve as it intersects Unit 1. And if you take this back into 2016 dollars, the congressional budget projection approximates to $14 million in 2016. And it turns out that that's 108 standard deviations past the curve. So the chance of this being fully funded was less than 1 in a trillion. And it works out that the maximal allowed first unit cost, if you want to get 100 of something, is closer to 11 million instead of 42 million. So I put up this post in January 2024 about the missile. It looks a lot like what you just saw there. And then 3 months later, they canceled the program. So these demand frontiers are limits that customers put up on programs, and they're not to be ignored. Now, the same thing works in commercial programs too. So in the early 2000s, a billionaire from Texas named Robert Bass decided he wanted to build a supersonic business jet. And he wanted to build 300 of these guys in 10 years for 120 million bucks each. So he had a decent cost proposal, had the right number of zeros. He thought it cost 4 billion, it might have cost 5 or so. Certainly wouldn't cost 10 times that. And if you did the value analysis, and we did, it was worth every nickel of 120 million bucks. Now, these guys launched with 20 orders, and so there was an upper demand frontier for the business jet market here that formed. So they launched for 20, and it shows that in that date, when they launched, they might have been able to get as many as 47 orders. And then 5 years later, they still had just these 20 orders. Now, the demand curve, the frontier was moving in the direction, went from 47 to 63, but as you can see here, it was still far away from where they needed to be. Now, this wasn't a 1 in a trillion shot, this was 1 in 40. So in December 2020, our order LinkedIn piece said they wouldn't get the 300 orders, since that would put them past their demand frontier. And then 6 months later, they collapsed. So all that's by way of saying that this demand function is pretty useful. Now, it also works out that demand applies to things that have the same function in different forms. So this unnamed spy satellite and this drone made by AeroVironment both perform surveillance, and so you might ask yourself, how might they be related? And so HypernomicA allowed us to combine and compare these databases. And so what we did was, when we combined them, we discovered that they had the same outer demand frontier. So we've got the spy satellites in blue, military satellites in green, and the drones, the UAVs, in brown, and they all have the same outer demand frontier. And very interestingly, they also have the same inner demand frontier. So this market suggests that if you're smart enough to get past the first unit, the government will guarantee you a certain minimum here. And very importantly, here you see this slope is highly negative. In this market, there's more money at the top of the market than there is at the bottom. So for example, there's 2 or 3 of these things being built here for 10 billion apiece. That's $20 billion. And these cost 15,000 apiece, and they've only made 18,000 of them. So this is several $1 million. So there's quite a bit more money here than there is here. That's different than it is in other markets. And so now we're going to shift over to costs. What we want to do is consider cost relative to value and demand. So one of the basic premises of Hypernomics is that for a product to be viable, its cost has to be less than its value, its sustainable price, and that when costs exceed price, the programs will stop. So nobody had picked this up from years ago. Turns out that Ford Motor Company had actually plotted their product demand. We're going to see what that means here in a second. Their price curve. This is the price over time, or I should say over units as they were going along. And they plotted their recurring cost curves. And when costs finally rose up to meet the price, that ended the program. And instead of saying that we have a equilibrium point in a market, we're saying at any point where prices exceed costs, as they have all the way through here, way past 10 million, I think 15 million units, as long as prices exceed costs, we have sustainable disequilibrium. If we want to work cost, value, and demand simultaneously, here's a little quick look at that. Here we created a sports car database of 1981 sports cars. We did this for the DeLorean vehicles. You'll see why here in a second. So we pulled 28 models and we looked at horsepower, quantity, seats, 0 to 60. And using our software, we discovered that the value of the car was this constant times the horsepower raised to this power times the quantity raised to this power. Now this becomes what we call a product demand curve, meaning that the more of your product that you put out, the less it's worth. And so these p-values, as you can see here, are both good, and the r-squared is 2. And so the BMW 528 came out in that year. The product demand slope for this is here, is that we take the actual price that it posted was here. We take its features and we plugged those features into this equation, and we get this green curve here. And you see that the green curve intersects this demand frontier right about here. This is how much they sold, so just a little bit past that. But this is the demand frontier of the entire market, and it approximates a 61.5% learning curve. The slope of their product demand curve approximates an 87% learning curve. And here what we've shown is if BMW had an 86% learning curve, they're making this amount. Now, of course, if their learning curve was steeper, which is to say if that number was lower, this difference would be greater. If they had a flatter curve than that, then they're starting to either run out of profit, and eventually this curve can intersect this curve here. That would be the end of the program. So the DeLorean came out in the year that we did this study. Basically, you can go back into time and figure out these data points, which I did. DeLorean came out in 81, ignored these forces, and they went bankrupt. So that's the reason that we study this stuff. What we're going to do now is we're going to cut over to a different window here, and we're going to look at the actual HypernomiicA software as it could be used to create an analysis here. So here are those data points that we created for 1981 car market here. Here's a scatter plot of their data. So there's the horsepower, here's the quantity, here's the price. So you can see as horsepower goes up, generally the price goes up. 0 to 60, the faster you go, the more you're willing to pay. So that's got an inverse relationship. Very interestingly, seats, that people wanted fewer seats in a sports car. And what this let us do then is you can pretty quickly plot a curve here. We'll choose a power form equation and we'll do this. So pretty quickly what we can do is discover that price is a function of the horsepower. So we have a decent relationship here. And it's also a function of the quantity. And so as you can see here, this lets us get an answer pretty quickly here as to what's going on. Now what this also does is there's a algorithm in HypernomiicA that works out what we call aggregate demand here. Aggregate demand is taking the total quantity and the average price in a series of bins here. So in this case, we made these bins in a geometric fashion. We could take and make them equally sized, or we could show them in a Fibonacci series here. And what we're trying to do is we're trying to figure out if we can get this is correlated to 96%. And then the demand frontier is actually a function of these points that you can select here. So you have a selector deselector here that allows you to figure out the actual limit of the market here. Now, what we noticed in this market and what we notice in most markets is the outer limit of this market is usually very often related to the demand frontier, which is to say their slopes can be virtually identical. We find that happens in the stock market all the time. And so if we make a 4D plot of this, then what we discover is that we have the value of the vehicle goes up with horsepower. So what you're seeing that here. So as horsepower goes up, the value goes up. But then as the quantity goes up, so here's the quantity going up, the value goes down, which relates back to this demand curve that we showed you here. Now I want to open up one more file here to show you how this would work in another market here. So we're going to look at the market for the helicopters. And so what we've done here in the helicopters is we build a whole bunch of equations. So every time you make an equation, you can copy it and save it. And so what we've done here is we've created a series of equations in various different formats that you can use to see how the market reacts to certain features. And so what we can do is we'll just take a helicopter group that we want to model here, which might be the corporate. and say we decide we want to look at interior useful load. And again, we instantly get a very good equation here that's already correlated to 94%. Now, what we might want to do if we didn't know what we're doing is we might want to do add passengers. But if we add passengers, you'll see the interior useful load and passengers are highly correlated. So it gives you this flag here that this is past the threshold that you've picked. So you might want to take that out. And then you might want to go down and say, well, I want to maybe take a look at the number of engines that I have here. And that turns out to be a helpful thing. That's improved the correlation. And then you might say, I want to look at the main blades as we did before. Well, that helps out. And you might want to look at cruise knots. And that adds to that thing. And then you might want to see if it has night vision goggle capability. And by golly, that works too. And then you might want to do a selector between a piston engine and a turbo shaft engine. This thing has a scrolling function here. And now what we have down here is we have the standardized residuals for all these helicopters here. And so what you might be able to find is that there are certain helicopters that are, in this case, underpriced, and then there's ones that are overpriced. So if you're a buyer, you might want to use this to quickly go off and say, well, there's an Airbus helicopter that's relatively underpriced, over 1.5 standard deviations. This is a Robinson helicopter. It shows being underpriced, but it's a Robinson, and they have a higher crash rate, and crash rate's not been considered by this. So you can just use this to figure stuff like that out. So as I said before, this selector lets you select any axis for any other. So what I'm doing now is I'm changing it from utility dollars to corporate dollars. And we discovered that it goes up with internal useful load and that it should go up with engines. So here we've got a helicopter that's nominally going 150 miles an hour, 2 main blades, 1 engine. And let's give it 5,000 pounds of internal useful load here. And you see it's worth 3.3 million. Well, if we give it a second engine, you see the price instantly jumps up here. And if we give it more main blades, the price jumps still. If we take the speed up, we take this here and we'll swap out this axis here and we'll put this cruise knots. If we take the speed up or down, the price also varies. And then we give it the ability to have these two different night vision goggles and pistons and turbines. Make that all true. And now we've got a helicopter that's worth this amount. Now, this particular market, we still have a pretty decent aggregate market in Frontier, but the selector automatically picks the outermost point in a certain market. It turned out that we've discovered since then that there's an upper frontier and an outer frontier, and sometimes it pays to put those two things in different buckets, and we'll show you that in another webinar coming up here. This is pretty well correlated too. Let me show you one more real quick. Here's some stuff we did for spy satellites. This is the final equation we have here. And what we've got here is that the value of the spy satellite is a function of the payload, speed, altitude, and quantity. And here we're seeing that the value goes up with max speed in this direction and also goes up with max payload in this direction. So in summary, we've got these unique insights that you can use in a variety of different ways. We've been verified through a bunch of papers. We have a patent on our software. We've had these Fortune 500 clients. We just had a book that came out. And we're going to start putting up classes and offering the software for sale. and we'd like to work with you.
So, Doug, first, thanks for doing this. In the meantime, if somebody is interested in working with you, how does that work? Do they come to you and basically you do all the consulting?
Well, we could either do the consulting, or as we've done several times, we could give them the training in the software and actually have a viable way of figuring out how to work through their market. So that's where we're actually switching our primary focus from consulting over to teaching people how to use the software so they can use it for themselves.
Fantastic. How long do you think it would take somebody to become pretty proficient in your software?
Well, we're going to have two different levels of classes, Jerry. So we're going to have a 3-day class where we teach for 4 hours and we give people homework. And then we're going to have 2-week class where we teach in the morning and we have homework in the afternoon. We come back and look it over, and they're going to be homework at night. In about 2 weeks, you can become pretty proficient. But I've been doing this for 13 years and I'm still learning stuff. So there's always something more to know, it turns out. So for example, that stuff where I was showing you the product demand curve in my book, if I can pump that for a second,
Sure.
there's I think 7 or 8 or 9 different ways to look at demand. And this product demand curve is crucial if you actually are in a market like DeLorean was back in 1981. There was enough market data for him, had he had our software, to know that there was a product demand curve, a value response service, and an overall demand curve, and also a cost structure that he needed to make. Now, he failed on all 3 things. He failed on cost. His costs were very high. He guessed wrong on value. He put in a 130 horsepower engine and it was asking the price for a car that would have had 100 more horsepower. And he guessed on the quantity wrong too. So he guessed wrong in every way you could guess. And the reason that the operative word there is that he was guessing. So had he had the software, he need not guessed, and he would have come up with something that would have been viable.
What do you think would be the number one lesson learned from your customers? And that could be tough because it's. I mean, just DeLorean seemed like he probably had 3 or 4 lessons he should have learned.
Well, the number one lesson is to don't guess when you could spend some time up front. Our analyses can it can be pretty hefty. They can start at low 5 figures and go into the mid 6 figures for a decent analysis. But you look at the case of that business jet that I was showing you there. That guy basically torched $2 billion. That missile, that was a $1.7 billion program. That missile will never be used in combat. That money was just lit on fire. So why spend billions when you can spend tens of thousands or hundreds of thousands to figure out what it is that you can do? Now, having said that, the hypersonic missile market has a very flat demand curve. And so if you were to make the missile very much smaller and have the range very much lower, you can make a viable missile. You can make tens of thousands of them. And people say, well, I don't want my plane to be in harm's way. I said, well, you can't really have it both ways. And plus, we made our planes stealthy. So if they're stealthy, why not take advantage of that, run them in as far as you feel comfortable, and make a missile that launched from 100, 200, or 300 miles instead of 1,000 miles away like the Arrow was. And that would have been the lesson that I would have given Lockheed Martin Skunk Works had I still been at the company, telling them what to do on the Arrow missile, because that missile at $42 million for the first unit, that costs as much as a Gulfstream jet.
We're going to wrap it up real quickly here, but do you have a contact name, email address, or anything you want to share, phone number you want to share?
Yeah. You can contact me at D Howarth, that's DHOWARTH at hypernomics.com. You can just write me directly. Or once you've maybe sent me a note, tell me you're going to call, so I know it's not spam, you can call me at 661-713-7531.
Thanks a lot again, Doug. Always learning something from you. Thanks again, and everybody have a good day, and happy Thanksgiving to those that are in the U.S.